Hello. Before we begin with understanding the frequency response of amplifiers, let's quickly talk a little bit about frequency response for a system in general. So let's think about a linear amplifier. A linear amplifier with some gain A, right? Let's consider that. Now, if I apply a sinusoidal time varying signal to its input, say Vi sine omega t, then the most generic fashion, what's going to happen is that this response of this amplifier is typically frequency dependent. In other words, what you're going to see is the output is going to look like some V naught sine omega t plus phi. Right? So a linear amplifier is going to basically amplify the amplitude or change the amplitude, and the amount of change in the amplitude is going to be, in the most generic case, frequency dependent. In addition, you are going to introduce a phase signal or phase difference between the output and the input. And again, this phase difference also typically is frequency dependent, right? So we say that in general, the gain of the circuit is a function of the signal frequency and can introduce a phase difference, which is also a function of the signal frequency. Now, in general, the system can be described by a transfer function. So suppose I define an output voltage and input voltage. I talk about a transfer function, which is the relationship of the output voltage to the input voltage, and it's typically defined using a complex function, and it's denoted either using the symbol T of j omega or H of j omega. And again, we'll see omega is the signal frequency, input signal frequency, or the frequency at which you're studying the behavior of the amplifier, right? And we use the complex term because we are dealing with sinusoids, which are nothing but exponentials. Now, therefore, if you think about the transfer function, in its phasor form, I can think of it at some amplitude, which is denoted as modulus of h of j omega, and an associated phase difference or phase information, which is denoted by the angle of j omega, h of j omega. So remember, this is, in general, h of j omega is going to be a complex number. So it's going to be defined by its phasor representation, which is the radius on the complex plane and the angle from the real axis on the complex plane. Now, what causes a frequency response? So if you think about purely resistor circuits, right? A resistance is a component which does not change as a function of frequency, right? For example, suppose I apply a 1 volt signal. If it's a DC signal, if I apply it across a 1 ohm resistor, I'm going to get a current of 1 ampere. If I apply a 1 volt sine 1 hertz signal across a resistor, I'm going to hit a 1 amp sine 1 hertz signal across the same resistor. So the response, if I had a purely resistor circuit, the response of that circuit is going to be independent of the frequency, in that the impedance that a resistance brings to a circuit is independent of its frequency. And so what you're going to see there is that the frequency, the response of the circuit, the response of the system is independent of frequency, or it's constant across all frequencies. What you also see is that because it's a purely resistor circuit, the output signal is always going to be in phase with the input signal. There's no phase lag or phase lead between the input and the output. Now, when does a frequency response come in? That comes in typically, when we've done basic electronics, that comes in typically when we bring in inductors and capacitors in the circuit. And why does it happen? Because both inductors and capacitance give an impedance that is dependent on the frequency, right? So the current voltage relationship of the inductor and the capacitor depends on the frequency, right? And so if you think about the impedance of a capacitance, it's 1 by omega c. The impedance of an inductor is 1 omega L. So what this tells you is at DC, when omega is 0, the capacitance is an open circuit, right? In the sense that it offers an infinite impedance to the circuit. On the other hand, the impedance offered by an inductor at omega equal to 0 at DC is 0, which means it's a short circuit. When you go to very high frequency of operation, at high frequency of operation, the impedance offered by the capacitance drops. So that approaches 0 as omega tends to infinity, whereas the impedance offered by the inductance turns out to be very large, so it approaches infinity. So the capacitor and the inductor reverse its roles, right? They're capacitances are open circuited at zero frequency, they are short circuited at high frequency, and the inductors behave in the opposite fashion. Now, to understand the frequency response of any circuit that we'll be doing, we need to first find the transfer function of the circuit. And we typically do that in what is known as the S domain or the phasor domain. Now, what is S domain? S domain typically means that we're doing analysis for sinusoidal inputs. Now, as you've done in some other classes, your basic signals and systems classes, you know that any signal, any time varying signal can be denoted as a sum of sinusoids using the Fourier series expansion. And so therefore, if you study the response of a system to a sinusoid, you basically can find the response of the system to any time varying function, right? And sinusoids are special because they give you an impedance of capacitors or inductances which are easy to work with. And so analysis of sinusoidal signals become very easy, right? And that's why we use the S domain analysis for such a system. So how does this work? We replace all the capacitors C with an impedance 1 by SC. Replace all the inductors L with an impedance SL, and then we use KCL and KVL to find the relationship between the input and the output signal as a function of S. Now this S is nothing but the representative of the signal frequency, and we'll talk about how S is related to the frequency in a bit. Now let's think about what happens when we connect systems in series or in parallel. So suppose I have two systems, H1 and H2 connected in series, and if I want to find the combined transfer function from X to Y, so X is the input signal, Y is the output signal. Again, you see this S denotes you're doing this analysis in S domain. So what we see is that the effective transfer function when you connect two systems in series is going to be the product of the two transfer functions. So it's going to be H1 of S into H2 of S. Similarly, if you connect them in parallel, that is, if the same input goes to both H1 and H2, and then the output signal is got by summing the outputs from these two systems, then you essentially have the effective H of the system given by the sum of the transfer functions of H1 and H2. This is intuitive and simple to understand. Now let's look at a generic transfer function. So if you think about a circuit, right? As we said, we replace the capacitors and inductors with 1 by SC and SL, and then we'll solve for some output voltage by input voltage or output current by input voltage, vice versa, whatever the case may be. So you're going to get a transfer function which is going to be generically of the form of the following format. It's going to have a numerator which is a function of S and a denominator which is a function of S. And because we're dealing with circuits in this set of videos, the coefficients of S in both the numerator and denominator are real because we're dealing with measurable resistors, capacitors, and inductors, right? So you have an M order polynomial in the numerator, say, and an N order polynomial in the denominator, where the coefficients all are real numbers. So I can also think of this H of S, since these are polynomials, I can think of them as a product of the roots, right? So I can factorize these polynomials into M roots for the numerator and N roots for the denominator. Now obviously, because A and B are real, these roots can be either real or complex, right? So they can be either real or complex numbers, but what you see is that the numerator, if it's an mth order polynomial, it's going to have M roots, and the denominator, it's an nth order polynomial and it's going to have N roots. Now the roots of the numerator are known as the zeros of the system. That is, when S gets to one of the zeros, when S becomes one of the zeros of the system, the transfer function of the system goes to zero. So we're calling out some specific S values. We'll see later specific frequencies for the circuit where the circuit response is important to know, right? So when you look at a zero, when the input signal has a frequency equal to the zero of the system, you're going to see that its transfer function essentially vanishes. On the other hand, when you look at the roots of the denominator, when s approaches one of the roots of the denominator, what you're going to see is that the transfer function blow up. In other words, the magnitude of the transfer function is going to go to infinity. And it's important to remember here that poles generally tend to be an important parameter because poles determine the stability of the system. Now, as I mentioned, because a and b are real numbers, the poles and zeros can be either real, and if they're not real, they're going to be complex numbers and they're always going to appear as complex conjugate pairs. So they're going to have the format a plus jb and a minus jb. Now, typically when we analyze systems, we do what is known as a pole zero plot, in which we plot the poles and zeros on the complex plane with the real axis along the geometric x-axis and the imaginary axis along the geometric y-axis. Typically, when we draw zeros, zeros are denoted by open circles and poles are denoted by cross. Now, poles are important to know because poles determine the homogeneous response. What do I mean by homogeneous response? It determines the response of the system or the impulse response of the system. Right? So it's determining what happens, how the system behaves when there is no stimulus applied to the system. Right? So it kind of shows you how the system will either decay or blow up if I slightly disturb the system. And the homogeneous response is given by the roots of the denominator because you're applying an impulse as an input. And the roots of the denominator are nothing but the characteristic equation of the system, right? And the roots determine the time domain analysis of the system. If you remember first order, second order circuits from your basic electronics class, these determine the roots of the system, the way the system is going to respond when it is disturbed from equilibrium or when I push it and apply a stimulus and move it to a new stable state. And so in the generic case, if I look at the output of the system in time domain y of t, it is given by a function or rather a sum of the various modes, if you will, of the system. And these modes are nothing but determined by the poles of the system, right? So every pole of the system denotes a specific node, and the output of the system when I don't apply any input is given by the sum of the nodes, a weighted sum of the nodes, where the weights of each and every mode, if you will, of the system is determined by the initial conditions that you've applied to the system. So now let's look at the pole zero plot. Now suppose I have a pole which is, so typically when you look at a pole zero plot, you think of it as a left hand plane and a right hand plane. Now suppose I have a system which has a single pole, a negative real single pole. What you see is that system, basically the pole is located on the negative real axis, and a real pole on the left hand plane, if you will, indicates that the response of the system is going to be an exponentially decaying component, right? So this shows you that the system is going to eventually decay and the output is going to settle to some zero after a long time. Now how fast that decays depends on how far the pole is from the origin. If there is a system which has a pole right at the zero of the complex plane, then that essentially means that the output is frequency independent, or the output is a constant in amplitude, and it basically depends on your initial conditions. Now on the other hand, if this pole now moves into the right hand part of the plane, that is when the pole is a real number on the positive axis, what you see is that the output response is a response that keeps blowing up in amplitude, which means that it tells you that the system is unstable because the output keeps increasing as a function of time. Right? So we'll see that we want to design systems, or we'd be interested in systems which are not unstable. So I want them to be stable, which means I want my pole to lie on the left hand plane. Now what happens, so as I said, the poles and zeros can either be real numbers or complex conjugate pairs. So let's look at what happens suppose the poles form a complex conjugate pair on the left hand plane. So if I consider two poles which are going to be formed as complex conjugate pairs, which means they have the same value on the real axis and positive and negative values on the imaginary axis, this system essentially shows a sinusoidal decaying response, right? So here what you see is y of t, instead of dying down exponentially, has some sort of oscillation, right? Eventually these oscillations subside and the output of the system goes to zero. Again, how fast the system decays as a function of time will depend on how far these poles are from the origin. Now let's look at what happens if the complex conjugate pair goes onto the right hand part of the plane. Now when it goes on right hand part of the plane, just similar to what happened when you had a real pole on the real axis, you see that the output is an sinusoid whose amplitude keeps expanding. So again here you have a system that is essentially unstable because the output keeps increasing as a function of time. And again, how fast it increases depends on how far these poles are from the origin. Now, when you have a system where the two poles lie bang on the imaginary axis, that means that the output is a sinusoidal output, right? Because you have a plus or minus j omega, e of j omega is going to cancel with minus e of j omega, so you're going to get a sinusoidal output whose amplitude is set by the initial conditions of the system. Now, when you think about system stability, therefore, an nth order linear system, when I say nth order, this order is determined by the number of poles it has or the degree of the polynomial in the denominator. So if you look at the degree of the polynomial in the denominator, if it's of degree n, it means it has n poles, right? And what we want to ensure is that for a system to remain stable, we want to ensure that all its components in its homogeneous response decay to zero. That means when t tends to infinity, sorry, this should be t, when t tends to infinity, sigma of I equal to 1 to n of ci e power e pi t should tend to 0, which means individually all these exponents to tend to 0, which means that all poles must have negative real parts. So if I want a stable system, I want to ensure that all my poles lie on the left hand part of the pole 0 plot. Now let's see how to look geometrically at the value of a transfer function. So again, we won't use this very often in this class, but it gives you an intuitive understanding of how h or the transfer function should respond for various frequencies. So let's consider a generic transfer function, right, which has m zeros and n poles. And we want to find the value of this function at some random s, which is given by sigma plus some j omega. Right? So remember that h of s can be written as some magnitude of h of s with some phase information. So that's the magnitude, that's the angle. Right? Now if I look at the complex plane, right? Suppose I had a pole on the real axis, right? Some pk. And suppose I'm looking at the value of the function at some s, right? So if I look at s minus pk is nothing but the vector that is drawn from pk pointing towards s, right? Which means if I define some ss sigma plus j omega, in generic case if I define this pk as some sigma k plus j omega k, then s minus pk is a vector whose magnitude is given by the square root of sigma minus sigma k the whole squared plus omega minus omega k the whole squared. And the angle it makes with the real axis is given by tan inverse of the omega minus omega k by sigma minus sigma k, right? In which case, if I now look at the h of s, magnitude of h of s of the system, all that means geometrically what I have to do is once I locate s, I need to estimate the distance of s from the various zeros and poles of the system, and then the magnitude of h at that point s is given by the product of the distances of s from all the zeros divided by the product of the distance of s from all the poles. And similarly the angle, again if I'm going to sum up all the angles, so it's going to be given by the sum of all the angles to zeros minus the sum of angles to all the poles, right? And so what you see here is geometrically I look into the pole 0 plot and I can find the value of h of s. And basically the magnitude is given by the ratio of the products of distances to zeros to the products of distances to poles, and the phase is given by the difference in the sum of angles to zeros to the sum of angles to poles. So which means that suppose I have let's look at a generic system, right, which has two poles P1 and P2, right, denoted here as a complex conjugate pair and a 0 Z. Then in that case, if I want to find the value of h of s at some value s, then all I need to do is draw the vectors from these poles to this point s. Let's call the distances as q1, q2 and r1. So q1 and q2 are the distances of s from the two poles p1 and p2. r1 is the distance of s from the 0 z. Then the magnitude of h at this point s is nothing but the ratio of r1 to q1 and q2, the product of q1 and q2. Right? So this is going to be the magnitude of h of s at this value of s. And to find the angle, I need to basically find the angle of the various vectors. So if the angle of the vector from s to z is say phi 1, and the angles for the vectors from s to p1 and p2 are theta 1 and theta 2, then the angle of h of s at this point s is just given by phi 1, which is the angle to the 0, minus the sum of angles to the poles, which is theta 1 plus theta 2. Now, why is this important? Now let's come back to our circuits and say that we are looking at what happens when you have a sinusoidal excitation. So typically we are going to be dealing with S values which lie on the imaginary axis, right? So we're going to be dealing with signals who have a sinusoidal input, right? So let's assume that there is a single pole system we have with a real pole in the left hand side of the plate, and we want to see how does h of s look as omega varies from 0 to infinity. So as I move omega from 0 to infinity, I'm basically moving my s along the y-axis, right, in the pole 0 plot. So if I now look at this point, at some point s initially some omega, this is the distance. So if I want to find the magnitude of h of s, the magnitude of h of s at this point is given by 1 by the ratio of this distance, right? There are no poles in the system. And the angle is essentially given by the angle of this vector to the real axis. Now, when this point moves farther away from 0, what's going to happen is essentially that the magnitude or the distance between s and this point increases, which means that the magnitude of h of s drops. So as I moved from this point to this point, s moved farther away from the pole, and hence the magnitude of h of s dropped. And similarly, if you look at the angle essentially also increased, right? Or in other words, the magnitude of the angle increased. So what you see here is that the angle so as omega moves away from 0, we see that h of s continues to drop monotonically, and the angle continues to increase till it hits pi by 2. So therefore, if I'm now going to plot h of s, so what you see is h of s monotonically decreases as this s moves away from 0, and the angle continuously keeps decreasing, because remember it's a pole, so I have to do zeros minus poles. So initially this was some theta, this theta increases, so the angle of h of s actually goes from minus theta and keeps on increasing. So when this is very far away from the origin, you're going to get this as pi by 2. So what you see here is, therefore, if I plot modulus of h of omega versus omega, I'm going to see a function that's going to monotonically decrease and eventually go to very small values at very high omega numbers. And similarly, if I look at the phase information, the phase initially starts off 0, and quickly as you go to higher and higher omega, this phase moves towards minus pi by 2. Okay. Now let's look at a system. What happens? Suppose I have a complex conjugate pair, right? So when I have a complex conjugate pair, again, I have two poles. So the magnitude of h of s at this point is given by the 1 by the product of these pole distances, right? And so here, when this pole is between 0 and one of the complex conjugate pairs, I'm going to have one number which is going to be less, one number is going to be slightly more. So there is going to be, so as this point moves from 0, you see that the product is going to decrease to some point and eventually keep increasing. So what you see is that as this point moves away from the origin, right, and as it crosses one of these points, you basically begin to see that the product keeps increasing. So in other words, the magnitude is going to keep decreasing. And furthermore, what you see is as this point moves away from the origin, because I have two poles, I'm going to have a pi by 2 from here and a pi by 2 from here, leading to an angle of h of s, which is going to be minus pi by 2 and minus pi by 2 or minus pi, right? So what you see therefore in such a system is you're going to have an h of j omega, which has a peak somewhere near the complex conjugate pair, and then eventually it falls down, right? So this looks like a band pass filter, if you will, right? And similarly, if you look at the angle of h of j omega, it again starts increasing slowly. Eventually, it's going to fall and asymptotically approach the value of pi, right? Minus pi, because I have two poles. So each pole is going to contribute minus pi by 2. Eventually, you're going to end up with the pole at minus, or the asymptotical angle at minus pi. So a few generic observations, if we look at this purely from a graphical point of view. If a system has more zeros than poles, only then the magnitude of the frequency response tends to zero at higher frequencies. If the zeros are more, then the gain becomes unbounded. So again, for a stable system, we want the poles to at least match the number of zeros. Ideally, you want more poles than zeros. That way you ensure that the system is stable and bounded. If there are a pair of complex conjugate poles near the imaginary axis, the magnitude has a peak or a resonance at a frequency that's close. So if I want to create a band pass filter, what's going to happen is I'm going to create a system which has complex conjugate poles, which ensures that the frequency response or the magnitude of the transfer function is maximum at some point and falls on either sides of that maximum. If the poles are purely imaginary, then I'm going to have a system which has infinite gain at the resonant frequency, and that would be a resonator. So if you think about a basic resonator in physics, that would be a system which has infinite gain at resonant frequency. Similarly, if I have a pair of complex conjugate zeros near the imaginary axis, I'm going to have flip of this, which is basically the magnitude is going to have a notch at a frequency close to zero. So what I create is a band stop filter, if you will. And again, the notch frequency is going to be close to the zero frequency, provided the zeros are close to the imaginary axis. That is, the sigma number is very small. If the zeros are only imaginary, then you're basically going to have zero gain at the notch frequency. If I have a pole at the origin, that means I have infinite gain at zero frequency. Again, these are non-physical systems, but just purely from the math, it tells you that if a pole is at the origin, it means that the gain is infinite at zero frequency. And similarly, at zero at the origin means that the gain at zero is zero. Now, typically when we look at the frequency response of an amplifier, we use what are known as Bode plots. Again, we have looked at Bode plots in one of our earlier videos. A Bode plot is nothing but a log-log plot where we plot the magnitude of the transfer function in decibels. The way you find it in decibels, it's 20 log to the base 10 of the amplitude. So this is a log plot or a log axis, and I plot this against a log omega. So this is a log axis and this is a log axis. So when I plot this, typically the response of any amplifier circuit, especially ones that we'd be doing in our initial classes, is going to look something like this. You have a certain region where the response is flat. And so in this region, the gain of the amplifier is independent of the frequency. You see that the gain drops on either sides of this midband region, if you will. So there is the certain midband region in which the gain is relatively flat with respect to frequency, and the gain drops on either sides of that midband region. So we call out the specific gain as the midband gain of the amplifier. We talk about two critical points, the points at which the gain drops to AM by root 2. Now why root 2? Typically, if you look at the power in the power in the output is going to be proportional to AM squared, right? Because if you think about a voltage or a current, the power is going to be voltage squared or current squared. And so what you see here is that at this AM by root 2 denotes the point at which the power reduces to half. So if the power here was some P, the power at these points is going to be essentially P by 2. In which case the amplitude signal actually doesn't go down to half, it goes down to 0.707 of it, or 1 by root 2 times that AM. And we call out these two frequencies, and these two frequencies are known as omega L or omega H, or we define this particular band, if you will, as the useful band of the amplifier. So we say that the amplifier, if we want to use this amplifier in a condition where we want the gain to be relatively stable to frequency, we'll call out these regions omega H and omega L, and we'll say that within this region we expect the gain to be fairly stable as a function of frequency, and beyond those 2 points the gain is going to rapidly drop as a function of frequency. And this is known as the bandwidth. To be specific, I would call this as the 3 dB bandwidth. 3 dB because at these 2 points the gain reduces by 3 dB. Remember, 3 dB is half the power of the output. And a big figure of merit for an amplifier is what is known as a gain bandwidth product. That is the product of this midband gain times the bandwidth. So for a good amplifier, or for an ideal amplifier, you want this AM to be as high as possible, and you want this bandwidth to be as large as possible, right? So you want this to be as flat as you can for a wide range of frequency. So this product of gain and bandwidth turns out to be a very good figure of merit for the amplifier. Now let's quickly recall single time constant circuits, just because we'll be using that often when we look at amplifier circuits. So again, single time constant circuits basically are made up of one storage element or one inertial element, either the capacitor or the inductor. In this case, we're going to look at capacitances because for most parts our circuits are capacitor circuits. Remember, the MOS is a capacitive structure. Wires are capacitive. Pads are capacitive, right? Layers of metal are capacitive. So you'll see that we'll encounter a lot of capacitance as an integrated circuit. So we'll look at capacitance-based circuits. So I can think of two kinds of circuits, one in which you have a C connected across the output pins, and one in which you have a resistance connected across the output pins. In both these cases, the 3 dB frequency is given by omega naught or 1 by tau, which is 1 by RC. Now if you look at H of S in both these cases, in one case it's given by K by 1 plus S by omega naught, in the other it's given by Ks by S plus omega naught. And so if I write this in terms of j omega, right, when I'm looking purely at sinusoidal inputs, then I replace this S with j omega, so I have K by 1 plus j omega by omega naught, and here I have K divided by j omega naught by omega minus 1. And therefore if I look at the magnitude of h of j omega, it's given by K by 1 plus omega by omega naught the whole square. So here you have a amplitude whose value keeps dropping as omega becomes larger than omega naught. In this case, on the other hand, here you have an amplitude whose amplitude rises when omega is less than omega naught, and as omega becomes greater than omega naught, this term keeps dropping, right? So here you have 1 0 and 1 pole. Here you have only 1 pole in the system. If you look at the angular information, the phase of these two, one is given by minus tan inverse omega by omega naught. So here as omega starts from 0, this angle information goes from 0 to minus pi by 2. Here it goes from pi by 2 to 0. And so if you remember, in this kind of a circuit, if you look at transmission at DC, transmission DC is some finite value K. At omega equal to infinity, the output is shorted because the impedance of the capacitance goes to 0. And so here this looks like a low pass circuit where at high frequencies basically your gain drops to 0. On the other hand, this circuit has a 0 transmission at DC because the capacitor is open, and at high frequencies this capacitance becomes a short. So here you see a high pass kind of behavior where the gain at low frequencies is very small and the gain becomes a constant at high frequencies. So how do you construct a Bode plot given a transfer function? So it's simple. As we have looked at previously, the gain typically drops by minus 20 dB per decade at every pole in the circuit. So as you encounter a pole, the gain drops by minus 20 dB per decade. On the other hand, when you encounter 0 in the circuit, the gain rises by 20 dB per decade. Similarly, the phase changes by minus 90 degrees at every pole. So the way we draw the Bode plot, the phase angle essentially transitions from 0 to 90 degrees, minus 90 degrees across the pole. The 0 again is the opposite of the pole, so here the phase angle increases by 90 degrees. So you see that the phase transitions from 0 to positive 90 around the 0. So let's look at an example. Suppose I have h of s, which is given by some 10 divided by 1 by s by 10 cube plus 1 by s by 10 6. So if I look at this transfer function, I see the denominator has two roots. So which means I have two poles, one at 10 power 3 rads per second, one at 10 power 6 rads per second. Both are on the left hand side of the complex plane. So the gain at low frequency, right? If I look at when s is small, when s is small, these two terms go to 0. My h of s has a magnitude of 10. A magnitude of 10 in dB translates to 20 dB. So the gain at low frequency, that is when s is much smaller than 10 cube, is going to be 20 dB. So if I plot gain versus frequency, right? So here again, remember this is a log plot. So here the gain goes in dB. Remember in dB, even though it's linear, in reality the gain is dropping logarithmically. Similarly, I plotted as a function of frequency here. Every segment here goes up by a decade. So what you see here is I have two poles. One is at 10 cube and one is at 10 power 6. So at 10 cube, what I'm going to see is that I'm going to see the pole at 10 cube is going to cause the transfer function to reduce by 20 dB per decade for all frequencies greater than 10 cube. Similarly, for all frequencies greater than 10 power 6, I'm going to have this pole at 10 power 6 reduce the gain by 20 dB per decade. So if I combine these two, what I'm going to be is initially at small values of s or j omega, my gain is plus 20 dB. So when I draw Bode plots again, these are piecewise plots. So till I encounter the first pole, my gain is going to be at plus 20 dB. Once I encounter this pole is now going to start pushing the gain by minus 20 dB per decade. So this is going to push this gain by minus 20 dB per decade all the way till I encounter the second pole. Now the second pole is going to further push the gain. So when I encounter the second pole, the gain is now going to drop faster than before. And what I see is that the gain drops faster and it's going to drop by 40 dB per decade beyond 10 power 6. Right? Now if I look at the phase angle again, now I'm looking at, remember there are two poles here, which means that the phase angle is going to go to minus pi. So if I plot in degrees, it's going to go to minus 180 degrees, right? So again, what you see is if I look at the pole at 10 cube, the angle at 10 cube is going to be minus 45. The angle is going to go from 0 to 90 degrees as I go from 1 decade below, that is 100, to 1 decade above, that is 10,000. Similarly, if I look at the pole at 10 power 6, as I go from 10 power 5 to 10 power 7, I'm going to see this pole cause another 90 degree shift in the phase. So therefore, if I look at the phase, initially till I encounter the first pole, right? So till I encounter 10 squared, because that's a decade below the pole, the phase angle is going to be 0. It looks like a resistor circuit. Then the pole kicks in. When the pole kicks in, the phase angle drops to minus 90 degrees as I cross this pole at 10 cube. Then the phase angle again remains a constant till I hit a decade before the second pole. And now again, the effect of the second pole is seen, and so I see now the phase dropping by another minus 90 degrees across the 10 power 6 pole, eventually stabilizing at minus 180 degrees away from both the poles. Right? So given any transfer function, you should be able to plot the Bode plots for its amplitude and its phase. So in the next few videos, we'll look at amplifier circuits and we'll look at how to estimate its frequency response and how to plot the Bode plots for the same.